There we go. Hello, people of the internet. Okay. All right, so we want to write a matrix to represent the system, and then you use row operations to reduce it to row echelon form. So first, just writing a matrix to represent this thing. It's a 2x2 system, so the matrix would be 2 rows by 3 columns, right? And what does the first row look like? 2, 1, -11, and then 1, 3, -8. Okay, and our instructions are reduce it to row echelon form. So our goal is basically that. 1's on the diagonal, 0 underneath, right? That lower kind of triangular thing. So what we need to do is first focus on this and try to eliminate that, right? So eliminate this. Once we get that eliminated, we can just kind of scale everything down to get the, the ones on the diagonal. So with a 2 here and a 1 here, what do you want to do to eliminate it? We can swap rows. We can add or subtract rows together. We can scale, like multiply row by, constant, as long as a constant other than 0. What do you think? Okay, the top row. Okay, yeah. So you can take the top row, multiply by 1/2, or you could get to the same thing if you want to avoid the fraction thing by multiplying the second row by 2, right? So that you get those to match basically, and then subtract to get it to drop out. So I'm going to do let me take the bottom row up to 2 instead of the top row, down by 1/2, just because they're odd numbers and fractions and just that whole thing. So 2 times row 2, this would be 2, 6, -16. And then row 2 minus row 1. So row 2 minus row 1, 2 minus 2 is 0. And again, that was kind of like, that's by design. That's what we're trying to do. 6 minus 1 and -16 minus -11. -16 minus -11, so plus 11, so -5. Now at this point, I mean, through all of this, you have some options about what you can do. Kind of the most direct way to do this would be that I've got a 5 here, I want a 1, so just take row 2 divided by 5. And then, again, we could do a couple of different things. We're trying to get to at least row echelon. It doesn't tell us that we have to go all the way to the reduced one. Like, I don't have to get zeros off of that diagonal. You can if you want. This would be an easy elimination to do. Or I can just scale this so that that 2 turns into a 1, right? So I take row 1 and divide by 2. It's going to give you fractions, but who cares, kind of, right? They're not terribly messy ones. Let's just do that. Row 1 divided by 2. So this would be 1, 2, 1,
1/2, -11/2, 0, 1, -1 in the second row. That's row echelon form. So we're good to go. Again, if you wanted to do, reduce row echelon, you can take like row 1 minus row 2 and get rid of this, and then divide by 2, and get to the same place. This is good enough though. This tells us that y is -1, and if y is -1, then you can use that top row to back substitute and solve. All I actually asked you to do in the directions was reduce the thing, so like that's all you really have to do. Again, for something like an exam question, just make sure that you understand what this tells you about solving the system, how you can use that, right? Okay. We're out with that, McKinley? Good? Okay. Anything else from that stuff that we need to talk about? Hopefully everybody found the solutions in Blackboard also. I may have done, yeah, okay, so the version that I wrote up and put in Blackboard, I did a little bit differently. I did go all the way to reduce. So from here, we got to here the same way, but then I went ahead and eliminated that thing above also, and then scaled the thing down so you can see what that looks like too. And I went ahead and wrote down the solution, even though I didn't need to, because I don't even read my own directions. So take from that what you will. Okay. All right. I don't know what else you guys want to talk about. You want me to just do the quick like rundown of all the things? Is that helpful if I just speed read at you for 40 minutes? Okay. So kind of like major things. Why are those lines so big? All right, major stuff from test 1. And not really just test 1, but kind of all along, right? Is the idea of what a function is, right? If there's anything that's, kind of the big idea for the entire class and, in some sense, kind of math all the way up through like calculus, it's the function concept, the function idea, right? A function takes x's, turns them into y's, shows how two things relate to each other, right? When we talk about an ordered pair that shows up on the graph of a function, that's an x and a y value that are tied together. And as one changes, usually we think about, varying the x value, the independent variable, and looking at what happens in changes in the y value. That's why we write a function as like, y equals f of x. You change the x value and that produces changes in the y value. So it's two things that are sort of changing together. And in order to be a function, that needs to happen in such a way that one of these pairs with one of those, right? That's what it means to be a function. When you use like a vertical line test to check a graph or something, what you're checking is that each x value only pairs with one y value. So for the function concept, the like definition basically, vertical line test, etc. So if you're looking at a graph, you can use that idea. If you're looking at something like a table, you're looking for x values that only pair with a single y value. So if you have like repeats in the x values, you have a problem. Way back, 4 months ago or whatever, one of the very first things we talked about was, like a vending machine, you push a button, you want it to just do one thing, right? Or, what's the other example I used? If we, made a list of like everyone in the room along with their height, well, each person just has one height, but if we switch it around, probably there are two people that are the same height, right? So that would be a problem from a function perspective. Things like finding domain and range, of course. If you're looking at a graph, hopefully at this point you can do that no problem. Basically, if I take the graph and kind of crush it down onto the x-axis, the domain is everything that gets covered up. If I crush it onto the y-axis, the range is everything that gets covered up. if you're doing it from looking at an equation or something, we basically think of it as like stuff that could go wrong, right? Like you can't divide by zero. You can't have a negative under a square root. You can't have a negative or zero inside a logarithm. So if you're taking the domain of, I don't know, something like that, whatever else happens, this has to be bigger than zero, right? The radicand, the stuff inside, can't be negative because it's a square root, and the square root of the negative is not a real number. So you would just kind of take the inside of that root, set it aside, figure out where it's bigger than zero, bigger than or equal to zero, and that's your domain. Similar kind of thing works for a logarithm, right? It'd have to be strictly greater than zero there. For like a rational thing with x in the denominator, you can't let that be zero because you can't divide by zero. Maybe I'll just make a note of those things. No negatives under a square root. No negative or zero inside a log. And no zero. These are really good sentences that I'm putting together here. I don't know if you noticed in any English class, folks. No zero in the denominator of a thing because you can't divide by zero. Right, so those are basically like, you know, for purposes of what we've looked at in this class, those are the things that we need to avoid in finding domain. And if you go back through your old tests, like at some point I've asked you about each of those things, like find the domain of this log function. Well, you got to figure out where the inside would be zero or negative, and then, you know, avoid that or force the inside to be positive. In other words, let's see. These things both would have been in like test 3 material, the first one and the last one. The log stuff would be test 4 material. What it means for a function to be one-to-one. So being a function means that each x pairs with just one y, so it passes a vertical line test. Being one-to-one means that you can take that function and invert it or like undo it, right? And still get a thing back that is a function. So if a function is one-to-one, that means it's got to pass a horizontal line test as well, that like each y comes from one place. So a horizontal line test, or in other words, no y values, right? So again, if we take like all the people in the room and make a list of, you know, everybody's name and everybody's height, I can make that a function because each person just has one height. It's not going to be one, or it's almost certainly not going to be one-to-one though, because there's probably going to be at least 2 people that are the same height, right? So I can't like invert that. I can't undo it or swap x and y and still get a thing that's a function. That's a thing that we haven't, you know, haven't really touched on a lot. We've kind of like implicitly used it in the background a fair amount since then, talking about like exponentials and logs and why we can solve stuff and why weird things like plus or minus come up sometimes. But we haven't like directly talked about it a whole lot since then. Transformations, that's another thing that, you know, we've done some stuff with that kind of in the background, but maybe not directly, right? Stuff that happens inside, you know, sort of grouped in with the variable, affects things from a kind of horizontal perspective. Stuff that happens, you know, sort of outside the action, the square, the whatever of the function, affects things from a vertical perspective. So look back at, you know, that was like, I don't know, week 2 or something of class that we talked about that. Okay. Arithmetic and composition. That's another thing that we haven't done in a while. This was section 2.6. But if you have two functions, say f of x is 2 plus x and g of x is 3x minus 1, then doing something like f plus g just means you take f and g and add them together. And do whatever algebra you need to simplify, but you just do whatever it tells you, right? This says add f and g, right? So we're defining a new third function called f plus g, but the reason we call it f plus g is what it does is take f and g and add it together. Composition, though, is sort of a different thing altogether. You read that as f of g. And what that means is that you take g and plug it into f, right? So wherever x, the input, the variable, the argument, shows up in f, you replace that with whatever g is. So this would be f of 3x minus 1. And f says take a thing and do 2 plus that thing. So this would be 2 plus 3x minus 1. And then if there's stuff to simplify, you simplify it. So that's how composition works. Switching the order, so doing like g of f, would just do that the other way around. And you always kind of work from the inside out, right? So I replace g of x with what I know about g of x, then I put that into that and simplify. Okay? Familiar? Yeah. Why is what? Which one? This one? This one? Wait, sorry. This one? So this is composition, right? So you read that like of, so it's f of g, which means take g, which is this, and plug it into f. What f does is take a thing and give you 2 plus whatever that is, right? So if you plug in 5, it's 2 plus 5. Plug in a million, it's 2 plus a million, right? So f of g, f of 3x minus 1 would be 2 plus 3x minus 1, right? So the 2 plus part is coming from what f does, right? It's the definition of f. And then you're just replacing the x with whatever g is. Okay, I think absolute value stuff would probably be the other thing. Equations and inequalities. This was 2.5, 2.4, I think. Pretty sure. Absolute value stuff. So an absolute value function, the absolute value, like y equals the absolute value of x, that's a V-shaped graph that opens up, right? Because you take like y equals x, the straight line, you take the negative part and you flip it or reflect it back up, so you get this V-shaped graph that's opening up. Of course, you can do transformation stuff with that. That was one of our like standard, function types that we used when we did that back when we didn't know anything. And you can also solve equations and inequalities. Remember, you just have to be a little bit careful about how you sort of break down the absolute value, right? Because there are kind of two possibilities. So if I'm solving something like that, as we just about always do, just about everywhere, the first thing I would want to do is isolate that, right? Get the thing that I'm going to have to think about by itself first. So move the 2 over. And again, that's the same thing we do just about everywhere, right? Then I'm going to think about the thing that I have to think about, right? This absolute value, don't worry about what's inside it yet. The absolute value of something, an absolute value describes how far you are from 0, right? So what this says is that something that I don't know about yet is 3 or more steps away from 0, right? So on a number line, what that looks like is there's 0, 1, 2, 3, 1, 2, 3. Basically, whatever this thing is, it's out here somewhere, right? It's 3 or further from 0, right? So what we do to sort of split that up is to say, okay, well, x minus 1 is either 3 or negative 3, which means here that x is 4 and here that x is negative 2. And then again, the way I would handle basically every inequality anywhere is to, not negative 4, set it up on a number line and just test, right? So use that and check to see what happens for values out here and in between these and out here, right? So if I plug negative 4 into that, I get the absolute value of negative 5, which is 5. Is 5 bigger than or equal to 3? Yes. So this inequality is true there, right? If it's true for negative 4, it's going to be true for anything out there, because by solving the equation, I figured out the only places that it changes, right? So take something to the left of negative 2, plug it into the inequality. You can go back to the original thing or use this. This will be a little bit easier to work with. Plug it into that. Negative 4 minus 5 is negative 5. Absolute value negative 5 is 5. 5 is bigger than 3, so it's true here. If x is 0, 0 minus 1 is negative 1. The absolute value negative 1 is 1. Is 1 bigger than 3? No. And then 6 minus 1 is 5. 5 is bigger than 3, so yeah. So our solution set is everything out here and everything out here. Negative infinity to negative 2, union with, that's 4 to infinity. And the endpoint should be included because it was greater than or equal to. Again, that's pretty much the way you'd handle any inequality. Solve the equation first because equations are easier, right? Break the thing down, however you need to break it down. This is an absolute value, so that means sort of considering the positive and negative versions, and then deal with the inequality. All right, that I can remember anyway. That's pretty much test 1 stuff, unless I'm forgetting something. Test 2. The big thing was quadratics. At the time, I'm sure that felt like a newer and more, unfamiliar topic, but we have done a whole bunch of stuff with quadratics since then. So I hope that nobody is, too worried about solving quadratic at this point, right? Look at it, try to factor it first. If you don't see a way to factor it, fairly quickly, just use a quadratic formula, simplify the thing down. If there's some kind of root term that doesn't simplify, then leave it alone, right? So solving equations, factor or quadratic formula, quadratic functions. Make sure that you know how to find a vertex. If it's in, like standard x squared plus bx plus c form, then you got that little vertex formula thing that, oh shoot, that is on this, right? The negative b over 2a thing. So that's on the, that'll, I'll give that to you so you don't have to try to like memorize it or whatever. Completing the square. That's a thing that we did, a fair amount like in the moment, but haven't done it in a couple of months probably. Remember, that's kind of a very specific factoring technique, right? So complete the square to factor, I don't know, y equals x squared plus 8x plus 1 or something. Anybody remember how this works? It's kind of in the name. You're looking for a perfect square, but you don't have all of it, right? Completing the square. What you're doing is completing the square. That means there's a perfect square there, but it's missing something, right? So what you're working toward is some kind of thing like this, right? Where there's some stuff I don't, know outside of there, but we want to factor it. We just want to force it to factor as a perfect square. So if you think about sort of working backwards from here, a perfect square like this, you would take 2 copies of that binomial, right? Whatever is in the parentheses, 2 copies of those and multiply them together. When you do that, you have to FOIL things. When you FOIL things, because they're identical, that means the OI part, the outer and the inner parts are the same, right? So the way that you get into the thing to complete the square is you take the middle term, because that's what came from the OI part, right? The outer and inner parts of the thing, and you split it up. 4x and 4x. The completing part is that, again, we're missing something, right? So I'm gonna leave a little bit of space for that. If I think about that as the result of expanding a thing, right? If x squared plus 4x plus 4x plus a thing that I'm not sure about yet is what you get from doing a FOIL type expansion, right? Expanding a binomial. Then what did the 2 things you multiplied look like? X plus 4. X times x gives you x squared. X times positive 4 gives you plus 4x. Everybody see that? If this came from, the first part of this expansion, it must have been x times x. If this came from, this and this came from the outer and inner parts of x times 4 and x times 4. Okay, what would the rest of this be though? What would the last part of that product be? 16, right? 4 times 4. Okay, that's the completing part, right? The thing that you were missing, the reason that that square was incomplete is that you're missing the 16, right? So add the 16 in, but then you got to subtract it off also because it has to come from somewhere, right? So you can think of that if you want as add 16 to both sides, but then we move one of them over, or just, plus 16 to minus 16 is 0, so I'm not changing anything, right? I'm just like borrowing 16. This thing is the same as that thing, but written as a perfect square with some spare change left over outside. That's called the vertex form of the thing. So it's another way to get the vertex.
I can't really just read it off here when we use the negative b over 2a thing, but here I can see it because this is kind of a like transformation version, right? -4, -15 would be the vertex. But again, like if I ask you to complete the square somewhere, what I mean is, very specifically like this kind of thing, right?
Okay. So test 2, again, like we focused a lot on quadratics. So, I mean, make sure that you can solve a quadratic, make sure you can deal with quadratic functions, completing the square. Other stuff that was on test 2, complex numbers. So how do you handle simplifying something like that? 2 plus 3i over 4 minus I. Do it. Multiply. Multiply by what? Almost. The thing that we want to do, the reason that that's problematic is that imaginary numbers are like a weird enough thing, right? I certainly don't know how to divide by. So what we're trying to do is get the imaginary part out of the denominator. So we multiply, and we do look at the denominator, but the thing you want to multiply by is 4 plus I. That's called the conjugate, complex conjugate. You flip the sign on the imaginary part, because when you do that, if you do this multiplication, then in the denominator you get 16 minus 4i plus 4i minus I squared. The middle parts of that cancel, so that's why we switched the sign, right? So that you would have 4i and minus 4i, so that the imaginary part will cancel out. And then I squared is really -1. I don't know how to divide by 4 minus I, but I do know how to divide by 17. So this is sort of a means to an end to turn this from divided by a complex number, which is weird, I don't know how to do that, into divided by a real number. And then you just do the same multiplication in the top, right? So like, I don't know what that is, but you just do that multiplication and clean it up. This part though, that's you just kind of have to remember that that's the thing to do. But again, I think thinking about like the motivation helps there. I don't know how to divide by imaginary numbers. Okay, well, don't figure out how to turn it into a thing where you don't have to. And if you had done, because that's like thinking like, okay, I got to multiply by 4 minus I. That's a really common thing that like people do all the time. If you still have I in the denominator somewhere, then it hasn't done what you wanted it to do, right? So try to use that as a like flag that, okay, well, I need to adjust something. Oh, okay, well, I got to switch that sign, right? So it is that you want to use the denominator, but you got to change the thing. Okay. Polynomials, I would really focus in on the graph stuff. And so zeros, multiplicity, in behavior, all that kind of stuff. This was 4.1 and 4.3. So given a graph of a thing, say like that. How many zeros does it have? 3. Where are they? There, and there, and there. What are their multiplicities? Two. Why 2? Bounce it off. Yeah. Even means that it's going to sort of bounce off, right? Odd means that it crosses, and we're going to assume things are kind of as small as possible. So 2, 1, and 2. What does that mean about the degree of the function? 5. Right, because you add the multiplicities. So the degree of the thing is 5. Looking at the end behavior, this thing winds up pointing down, right? The ends are going opposite directions. That's if the degree is odd. Ends up pointing down. That means the leading coefficient's negative. So negative leading coefficient. It's got 3 zeros. You know, this is like x minus 0, but we don't normally write the minus 0 part. And each of those factors, because of the multiplicities, the x plus 3, the factor that goes with negative 3 shows up twice, so it's squared. The x minus 5 factor, well, it goes with this, it shows up twice, so it's squared also. So that would be, you know, a factored form of a thing that looks like that. Okay. All right. I think that's it for test 2 stuff. I think test 3, rational functions. So asymptotes, domain, intercepts. You know, given a thing, how do you find each of those things, right? You have vertical asymptotes that deal with places where the function's undefined. You've got horizontal asymptotes that deal with end behavior, what happens eventually. You got intercepts that occur when, you know, either y is 0 or x is 0. So there's sort of a lot to unpack in all of that. This is 5.1 and 5.2, where all that stuff it shows up. Of course, we did some, you know, solving things as well. Solving rational equations and inequalities. Find a common denominator and use it to get rid of all the fraction parts and then solve. And then the other thing we did in the test 3 stuff is dealing with radical and root equations and functions. Right, so if you have a square root, you do the opposite thing, right? So get rid of it by squaring. If you have a cube root, you cube to get rid of it. And then again, like there's some domain stuff attached to that we kind of already talked about earlier. And test 4, exponentials and logs, right? Solving equations, working with functions, most of that comes down at some point to taking an exponential and turning it into a log, or taking a log and turning it into an exponential. There are, the special like log properties kind of along with that stuff. To, expand or condense. application stuff, I would, mostly focus on the compound interest thing. We did some other things, but I would focus in on that part. And then this stuff that we talked about the last, week or so, the system of equations and matrices, and again, as I said yesterday, like expected to need to solve some like 2x2 type things. So similar to like the front of the thing that you did last night, those first two problems. And then for larger systems, think more in terms of like, sort of like doing parts of it, right? Maybe setting it up in the first place, or maybe if I give you a matrix that's already reduced, how do you interpret what that means, but not having to do like sort of the full thing yourself, because that's a little too involved for my taste, given where we are in the semester. Okay, so that's it, right? I know it's a lot. You got a lot of stuff to look over, a lot of stuff to think about. But again, you guys have a fair amount of time, but the flip side of that, this part doesn't need to be on the recording.